There we go.
Now. Okay, there we go. So, as Alex mentioned, thank you very much for everybody to attend, especially the panelists that are going to join us. So this is Jesus Tapia. This is I am the director of the business unit that we have within our business school called EASY. EASY was born in 2009, and in 2014, our CEO, with the vision of disrupting the educational model in this country, created a business unit called Impact Accelerator, and we are basically the main business unit dedicated to innovation and entrepreneurship. And one of the topics that we cover is a lot of experience in European projects. So that's welcome. Next one. Let me see if I can move this. Takes a bit of time, or it's not clicking here. Can you move it, Alex? Okay. So we have representatives of 5 different projects that are funded by the European Union, and all of them working in an industry that I was reading last week that is worth around $20 billion by 2030, especially the segment that we are covering here, to the safety and trustworthiness in robotic autonomous adaptation. So I'm going to leave them 3.5 minutes in a pitch format that we are very used to do here at EASD. So every one of them will present, hopefully in 3.5 minutes in a format pitch, their project. So I'm going to start with Peter, with RoboSapiens.
Thanks very much. I am the coordinator of the RoboSapiens project. Here you see the partners and the consortium, and we have been running for 2.5 years, and will be completed by the end of this year. Should be able to change. It does not seem to be working. Oh, there we are. Okay. I would like to show you the objectives we have of the project here. The first one is to enable control software of robotics in an open-ended self-adaptation setting, such that we can take unprecedented system and structural changes also to the environment into account, and then try to kind of ensure the safety of the robot and its environment during adaptation and after adaptation. Objective 3, this remote control does not seem to be working. There we are. Okay. Objective 3 is to try to use advanced deep learning techniques to actively reduce the uncertainty of tasks. And then as objective 4, we're trying to assure the trustworthiness of the systems using both the deep learning and kind of architectural means to kind of ensure that the robotics self-adaptation is possible. It's interesting. So if you look at the left part of this picture here, we have what we call a MAPE-K loop. Essentially, it's a matter of monitoring, analyzing, planning, and executing given some knowledge. That's the way you typically do autonomy. And if you want to change to a new version of that, you have a challenge in the sense that you need to recertify things every time. If you look at the right-hand side, is what we are trying to do in the the RoboSapiens project, where we try to take open-ended safety and make it trustworthy, where we have a legitimize phase after the planning to see if we are validating the safety of it. But in addition to that, we also have a trustworthiness checker directly on the controlled robot, just on top of the robotic control software. So there's a number of clicks required here. I don't know why this is not working. Yeah. So the new part essentially is to try to look at the safety constraints where we have some assumptions at the for each of the property that we are interested in making sure will be safety correct. And if you click once more, when we look at the trustworthiness requirements, we do what we call runtime checking, where we also check the assumptions being correct. But all of this needs to be done, if you please click once more, in the presence of uncertainties, because different sensors may have noise of different kinds, and that essentially means that the vision or the perception you have about the real world may be slightly twisted, and that needs to be taken into account. Yeah, next slide, please. So we have made a number of architectures from a conceptual state to a design stage to a realization stage. The different work packages in the project have different kinds of automations transforming architectures to different design things. You see the different types of arrows. Some of those are automated and some of those require user input. But in a sense, it's automated as much as possible in the system setup we are having, including things further down at the end, looking into the potential safety things we need to take into account and the uncertainty qualification metrics we need to operate with as well. That's all from my side. I'm happy to ask questions or answer questions later, but I'll pass over to the next one.
Okay, can you hear me fine? Yep. Okay, I'm Richard Duro I'm the PI of Pillar Robots project. Pillar Robots, I don't know who's moving things, but they're going too fast. I'm a professor, I speak a lot. Pillar Robots stands for Purposeful, Intrinsically Motivated, Lifelong Learning Autonomous Robots. So you can go to the next slide, I guess, because I have no control. Well, I do have control here, seems. Okay, so Pillar Robots is a consortium by people from many parts of Europe, including PAL, AI to Life as industrial partners, and then people from Athens, Sorbonne, the University of Coruña, and CNR in Italy. The idea is that we're trying to get robots to do lifelong open-ended learning autonomy, LOLA, we call that. But who wants a completely autonomous robot? I think nobody wants that, but you know, it's like having a completely autonomous teenager. Makes no sense. So we need some type of objective. Otherwise, it's basically random aspiration by the robot. So we want robots to be useful in real applications. To this end, we're using the concept of purpose. Purpose is a domain-independent abstraction of a goal or set of goals that expresses what the designer or the user wants. You know, don't hurt yourself here. Keep working areas tidy. Do, these very general objectives we always have. And we want to transform that into something that the robot can use to constrain the way it operates. The autonomous robot can use to do that. So basically what we're doing is leveraging and expanding the research on LOLA by the participating groups, introducing and developing the concept of purpose as a way to introduce the bias that is necessary to carry out the desires of the users or designers in this case, and then integrate LOLA and purpose in a cognitive architecture that can be tested in real use cases and actually tested in real application scenarios, which is the tricky part, as you all know. So let's see if this works. It's not moving now. I lost control. Okay, no, now it's going too fast. Okay, so we have 3 types of validation use cases in the project. A non-social domain, where purpose is given to a robot, but there are no people around, so the robot can make really bad mistakes without too much of a consequence, which is in the agri-food sector. Then we have the other end, a social domain, where the interaction of the robot is mainly with humans. So purpose has to be very well defined. And then we have a hybrid domain, which is an industrial setting where there are humans and non-human operations at the same time. And challenges we are having. Okay. The interaction with users for the extraction of purpose of what they want is it's been a challenge, especially the balance between just bothering the user too much to avoid misinterpretations and getting the right level of purpose definition. Then obviously cognitive architecture integration is always a challenge because of complexity, perception, and attention, and especially abstraction. You know, going from that high level user definition to what the robot concretely has to do. Real-time operation is a challenge when you have to do all this processing. And something we were not counting on, and we're having really huge challenges, is integrating this in the robot platforms, especially using ROS2. It's driving us crazy, completely crazy. But that's life. And that's basically it. Thank you very much.
Okay. Hello, I'm Matteo Saveriano, and I'm the coordinator of the Inverse project. And Inverse stands for Interactive Robots that intuitively learn to invert tasks by reasoning about the task execution. Let's see. Oh no, for me it works. Sorry. All right, so this is a little bit basically the idea of Inverse. So we have now robots that know how to perform a certain task, for example, an assembly. They can be programmed, they can be taught to perform the task, they can use reinforcement learning, whatever. And basically our key question is, can then the robot reuse this knowledge in order to execute the opposite task? And this has, of course, a big implication in, for example, manufacturing and other stuff, no, like for recycling and this type of things. And yeah, we were driven with this idea by somehow human inspiration. No, I mean, I think everyone has this basically memory. You know, if you know how to assemble something or build something, then when you have to disassemble it and then reassemble again and so on, you become smarter and smarter, right? Because you are able to reuse your previous knowledge in a different domain. And this is basically about the project introduction and its objectives. So we are now at 2.5 years. The project is a 4-year project, so we have still 1.5 years to go. So we want to solve complex manipulation tasks across different domains by synthesizing, monitoring, and executing inverse plans from direct task definitions. Okay, so we have basically a few ingredients there, and we want to, of course, understand the robot surrounding, to be safe, perceive the presence of human, the objects, changes in the environment, and this type of things. Represent the knowledge in a flexible way such that it can be reused, no, and maybe generate new knowledge when new data come, and continuously adapt, basically. So robots now, I mean, it's clear that if you want to work if you want to really deploy robots in unstructured environments, they cannot be static. They have to adapt continuously to changes in the environment, to new production flows, and other changes. And this is basically our key, let's say, scientific split of the project that we call the multimodal continual learning and execution loop, or the MOCL loop. So basically on the left side, you have some, let's say, state-of-the-art, more or less, technologies, although we had to develop some new things for the project. But yeah, the left side is kind of consolidated now. So we are basically able to take human-level instructions, text, images, CAD models, and through perception, reasoning models, and so on, convert this information into a knowledge base where basically all the robot knowledge about the task is stored. And then we can basically activate our continual learning loop where basically we continuously keep improving the perception and interpretation of the world and the action of the robot, and also, of course, considering human aware and safety constraints. And key challenges and open issues. So we are facing problems with task inversion. So task inversion is not that easy. If you think about, for example, plugging an Ethernet cable, no? Then when you plug, it's just like a pegging all task. But if you have to unplug, you have to click this little clip and then remove it. So very simple. So task inversion is somehow we found out that it's either trivial because it's the same motion repeated forward and backward, or extremely complicated. So there is no like nothing in between that. So yeah, we are now basically working a lot on this, and from the semantic level definition and how to basically define task inversion in a robust way. Knowledge base. Now, I mean, we are widely using, of course, foundational models, large language models, visual language models, and so on to populate the knowledge base, both for direct and inverse task. It works, but still there are some, I mean, hallucinations, less and less, I have to say. These technologies are improving now with in-context learning and agentic AI. It's much better, but still there are sometimes some inconsistencies, or they don't perfectly match the knowledge base of what people have developed in planning and things like this. So still we are on this. And integration, as my colleague, Richard said, it's surprisingly hard to integrate and deploy these robots in production environments, and we also rely on ROS2. ROS2 also became better and is becoming better and better, but yeah, then you have to interface with many other communication layers and so on. So it's quite a hard task basically to basically deal with. And I think that's the end of my presentation.
Well, my turn. Thank you, Matteo. Good morning to all. Yes, I want to introduce you EARASHI, that in terms of funding, I think that has nothing to do with the rest of the projects. And moreover, it's already closed. I mean, it ended a few months ago in February. So yeah, that's the reality for EARASHI. There was an embodied AI robotic application for safe human-oriented industry. There was a cascade funding project. And from EARASHI consortium, we have support 10 different application experiments, 10 different companies all over Europe in their deployment and technology development. I'm Ganis Lassa from Mondragon University, and I want to introduce to you in a few minutes EARASHI, okay? The aim of EARASHI was to demonstrate how AI data and robotic solutions can support work in the daily tasks. From Mondragon side, we were the responsible of tracking the impact and the adoption that this technology had in the implementation. And from EARASHI side, we have prioritized safety and security, ensuring the technological advancement, to improve not just conditions, but also reducing accidents and improving workers' well-being from an overall perspective. So, two pictures here. On the one hand, the consumption, and then the application experiments or the beneficiaries, right? That after 2 open calls, each company have been funded by 200K euros for the implementation and development of technology, and we have supported not just, but also from the human-centered design coaching that was implemented by Mondragon University. So what we did here, that was basically the objective was to improve, as I have said, the well-being at work, satisfaction, motivation, optimize processes, and also keeping in mind the productivity and quality of the processes, right? But keeping in mind all these ingredients, what we have done It's just to suggest an holistic strategy that was in a frame of human-centered design coaching together with a eco-sustainable let's say coaching, also the business coaching, right? And we have supported different sort of services. But what we did in the human-centered design coaching was just to discuss and support with each partner or each company, starting with very preliminary online webinars with very basic principles of this knowledge, and then we took with one-to-one individual coaching sessions all the skill gaining, and we have created an index that was a human-centered index. Industry index, just to track and get evidences of how they improve in a year and a half in their practices, right? We jump into the implementation, define the KPIs, right? And at the very end, what we did is to track and collect from the end user the adoption rates of the technology after implementation. And thanks to this EARASHI project, what it is public material is the two specific deliverables that are about human factors and UX handbook, and also guidelines for inclusive design and ethics in industry, right, that are available. And then the impact, and I conclude with all this, is that basically, as I have mentioned, we have support 10 startups and SMEs from EARASHI side. We have developed ACD training and we have created resources. All companies, they have implemented, despite their basis, let's say, to human-centered practices that was low or rather low. In the reality, at the very beginning, they have implemented tools, and then we have improved the product design and usability. There is, thanks to EARASHI and the coaching, a strong link between the social science, humanities, and technology at the moment. And we have increased, because we know the rates of the adoption at the moment for all the solutions on the market. We have increased the market readiness, right? So that's a very short wrap up of what is EARASHI. Okay, thank you.
Okay, so hi everyone, I'm Maximilian Navo, and I'm responsible of the integration of the software stack on the robots, so in the lab environment and in the case studies. And I'm going to present the AGIMUS project, which is next generation of AI-powered robots for agile production. Next slide, please. It's a 4-year project, and we are done in the end of this year, so September. This is the last month. The project is composed with 3 research partners. One is the last CNRS in Toulouse, France. The other one is INRIA in Paris, and then the last one is in Czech Republic. Is the Czech Institute of Informative Robotics and Cybernetics in Prague. For the industrial partner, we have Kublin International, who helps us organizing the project and managing it. Then we have Airbus Kliman and team for the case studies, and Robotics, who is responsible for 1 case studies and designing a robot prototype for the project. Next slide, please. So yeah, the idea of the project is that when you have a task on a robot and you want to let's say pick something up and place it somewhere, then you have to define a proper trajectory, and you want nobody around, and it's a really tiresome task to design properly these trajectories in constraints environments. And this is basically what it's done in the industry for safety reasons. And what we want to do is we want to break the safety nets. We want to have this let's say, easy to set up robots. We want to have robots to go from one chain to the other and be very agile in that sense. And that's what we aim at. So next slide, please. So we really want to have this like from robot sensor to a perception module. So basically perceive, plan, and act loop, which is robust enough and general enough so that each module can be put in different situation and they just work. So for the perception module, we want to have some kind of it's not exactly VLM, but it's still computer vision based, and we want to feed this computer vision model reconstructed of the environment into a planning module, and then we have a task planner that is more or less the user interface. So the user can say, okay, I want this task to be done, just do it. And then the task planner handles the organization of the logic and stuff. And all of that goes into the what we call predictive control module. The idea is to have a under the hood control that allows us to make the robot work in an infinite space. So we don't want one trajectory specific, but we want to have a tunnel of possible trajectory which are warranted safe. So we constrain the environment of the robot. We constrain the motion of the robot so that any motion that the robot can choose is safe. The next slide, please. Then we want to apply that into different case studies. Two from Airbus is so they have this cell in space. So they have this big satellites basically that builds satellites. So we have two-arm robots, and you have on the background some parts. You have in the middle some tool holders, and the robot can actively change tools, pick up parts, assemble parts, and then basically create satellites in space directly, not just on Earth we send it, but we actually build satellites in space directly. And then on the other side, sorry, no, just slide before, the second application is deburring. So deburring is when you drill a hole, you have some waste in it. You need to remove this waste and clean up the surfaces. That's deburring. So we just insert, it's pegging hole problem. We insert a tool inside the hole. The tool does this thing, and then we put it back. Next slide, please. Then we have two more case studies from Kleeman, which is an elevator company. They have this ceiling parts, which is basically big boards that are on top of the elevator cabin. And we have to put reinforcement parts. So we have to spread some glue and then put the bar and press it. So this one doesn't have any prototype with the robot, but we're actively working on it. And then so on the second image, you see that actually the Panda robot is a prototype where we can actually spread glue, and we can apply some glue and then spread it with the black tool that you see. Next slide, please. And then from Team, which is a packaging company, we have some carton board, sorry, and you have usually some pre-cutted places on the board, and you need to usually press it to remove it. So the idea is to identify the cardboard and then apply some pressure inside the waste of the pre-cutted places on the board and remove this waste, sorry. And so that's the first task. And then the second is you have this white clips that you need to insert into some cardboard again to prepare for assembly later. And the idea is to pick them up and insert them. And next slide, please. And then the last one is a case study where we just do, well, basically sorting. So pick up and place of a pile of object into dedicated boxes. And even if we can actually get further, it would be to insert objects into placeholders with the new AGIMUS Tiago prototype designed by Pat. And I think this was the last slide. Yes, thank you very much.
Thank you very much, everybody, for the very interesting project that we are all involved in. I have questions for everybody. I'm going to start my first question. I'm going to direct this question to Peter and Richard. In the practice of safety and trustworthiness robots, where do you think the current system, the current practices that are being put in place start falling apart due to the fact that the robot has to adapt at runtime? What do you think those challenges are, Peter and Richard?
If you want me to start,
yeah,
I can say a few things that in general, safety is a major concern with respect to robots, in particular when they are collaborating with human beings. I think that we need to be able to use runtime verification, but runtime verification for properties that dynamically can be changed because we have to adapt to the different circumstances. And that's what we are trying to do in our trustworthiness checker inside the RoboSapiens project. To what extent it's certifiable is another matter which we are discussing with certification authorities today. So it is tricky to be able to make it sufficiently trustworthy to be acceptable. We also have an SSH angle in our project, so we are having social scientists looking into what people think about autonomy in robots and how they want to tinker with them and stuff like this. So there are many challenges with respect to this, but I think if we just don't touch the challenges, we don't move forward with respect to things. So that would be my answer to your question.
Okay, thank you, Peter. Richard?
Okay, yes, I do agree with Peter in the trustworthiness part of things. When you have a moving target, you know, the robot is learning, it's adapting, it's changing. So whatever you certified when you started with is not what the robot is now. So that's a big problem, certifiability. And I think we have to change the concept of certifiability to the concept of trust in terms of delegation, you know, trusting the system to decide the way you think things should be decided, and not to do the things the way the things should be done, which is a different concept. That's one of the biggest challenges. But I think there's another challenge that is very, very important that we are not taking into account, and is the fact that to learn and to learn well, knowledge needs to be represented at different abstraction levels, which means the robots need to autonomously be able to generate different abstraction layers and to work with different abstraction layers at the same time. And that's, at this point in time, is not solved, not at all. I mean, not even close. Mm-hmm. And finally, my last point here is that within all this, we need to introduce some way of making the robots aware of cultural and ethical limitations, which is not trivial. You cannot just put rules in there. You know, what do you put in? The Constitution of Spain, or do you make it the Constitution of the US, which we've seen can be used for many very weird things. That's a very difficult question that is being addressed by many people, but there is no clear solution right now to how do you introduce, because when we're talking about cultural and ethics limitation, we're not only talking about rules and regulations, we're also talking about how we humans tend to do things together. You know, when you play with your friends, there are some intrinsic rules that you establish there, you know. So there are many, many things that need to be taken into account. So those are, to me, the big three issues.
Yeah, thanks, Richard, because I think you opened the next question and you spoke somehow. So let's go to the next question. I'm going to direct these questions to Matteo and Maximilian. So let's go start with Matteo. So once the robots began adapting at runtime, something happens all of a sudden. What is the hardest thing to guarantee on someone who is close by, or in other words, if I'm an investor and I have 10 million euros, where you would put those 10 million euros in one single thing? Where you put them to secure what? To secure explicability. We have the EU Act right now. Where? Matteo?
My bank account.
Yeah. So I would maybe, I mean, I'm a bit biased towards this, but I would put this on safety aspects basically, because I mean, when you adapt and the environment changes, you should of course reach some level of safety, especially if you have interactions. That is now a big topic, and you know, you cannot if you are co-working, if you are sharing the environment with other people, you cannot just you know, harm them. And similarly, basically, you cannot destroy the robot, right? With a very strong interaction with the environment. So I think this is something that we should definitely you know, implement in the robots, and without compromising the adaptation. So now there are all the safety standards and all the safety things that basically come, I don't know, from control theory and so on. They're often very limiting in adaptation. Okay, so safety doesn't basically go end to end with adaptation. It's a limiting factor sometimes for adaptation. So we should basically improve a lot on this. Regarding another topic like predictability and this type of things, I have mixed feelings about this, because you know, we do things because we have our own embodiment. Okay, so we humans do act in a certain way because of our embodiment, our sensing, our capabilities, our kinematics and dynamics and so on. And the robot is not has not our embodiment, right? So maybe the best thing that for the robot can be completely different from what we will do, right? And still work well for the robot. So predictability, you know, it's a big, it's also a big topic, but I would not really enforce strongly predictability, because this can be really, you know, not a way for the robot to learn how to adapt, basically.
Okay. Thanks, Matteo.
Thanks.
Maximilian?
Actually, a lot has been said already, so it's hard to bounce back. I do believe that safety is critical, and actually, when you're talking about adapting at runtime, I think what's the most challenge is deterministic predictability. Let's say in a traditional automatic setup, you have you're absolutely sure what the robot is going to do. There's one single trajectory that the robot is going to follow, and if it deviates even a single degree from that, there's like hard stop everywhere and and flashlights, and then the full system goes down. Now we want to have adaptability, so we want to have the robot to be able, as I said before, to explore an infinite space of trajectories, to go from point A to point B, and the robot is continuously recomputing time, recomputing its trajectory. So you want a system to detect if there is a fault or not, but you don't know what the robot is going to do. So instead of trying to imagine all the possibility of all the behavior of the robot, what we want to do, at least in AGIMUS, is to keep the adaptability but constrain its possibility of trajectory. So we want to have a guideline from point A to point B. That's the global motion planning that could be human design or optimized. But then during the launch time, we want to have the robot detect collision avoidance, self-collision avoidance, contact forces. So we really want the robot to perceive its environment in terms of physics. Would it be estimated collisions or current collisions? And this is where actually compliance and force control goes into play. And we want to not work with very rigid robots, but compliance robots. So I think safety goes into this direction, going to soft robotics, compliance robots, etc.
Okay, I was reading an article last week on autonomous driving. I'm coming from the automotive industry, and they call this smart anticipation. So you pointed out somehow that concept as well. So you remember that. So let's go to the next question, and this one I'm gonna direct this question to Ganesh, especially due to the fact, and this is something that we all know, that the European Commission is putting a lot of focus that all these advanced technologies that are mostly developed by universities, high-tech organizations, must come to the business. Okay, and in your case, Ganesh, you had the experience of moving these technologies into the real life in real companies. What have changed, and what are the challenges that you guys face in your experience when you try to move that technologies into the real world, so to speak?
Yeah, there are many. Yeah? There are many. Yeah, and then I guess that you can imagine even having a year and a half for most of the cases. Yeah, it was a matter of time as well. First of all, technological barriers, right? We are talking about integration of technology at different levels. We have suggested from the consortium side, together with the services that I have mentioned earlier, the building blocks, right? That was like packed technology solutions that different members of the consortium just try to support in the process of integrating the solution. Aligned with certain challenges and objectives, right? With the idea of improving the solution and the well-being of the operators or the workers in the real environment. What we have realized is that the earliest that you get the insights and the participation of the end users or even workers at different levels, the better, right? This is what we have learned in terms of when we are talking about adoption, when we are talking about how people is ready to use this solution in the market. Because at the moment, and different phenomena have been already listed or mentioned, but as far as we have identified, the perceived safety and controllability are the let's say the main challenges at the moment. We refer to the, at least at the picture that we get or that we got on EARASHI, right? Then it's true that we have learned from different realities. Then different application experiments have to do with different sectors, solution, technology, even the size of the company, and with different type of barriers in this journey. But that's it. I mean, mainly.
Wonderful experience, I guess. You guys have. Okay. So let's continue with the conversation. I don't know if someone has any questions out there, Alex. I don't think so. No? Okay. So let's go to the next one. I'm going to direct this question to Maximilian and Peter from RoboSapiens. How do we validate or verify behavior that evolves over time? And especially in these days that technology evolves rapidly, and circumstances and surroundings also change. So how you guys approach this, Peter and Maximilian?
Do you want to start or I start?
You go.
Okay. I go. So first of all, we want to do what every good researcher do. We re-implement state of the art, and then when we do a change in technology or change in stuff like that, we want to verify that the behavior is consistent with what was done before for a specific task, for example. And we validate that at least the behavior is growing in terms of capability. And then to verify it, I think it's I'm not sure about the validation and, well, I'm not sure about the word verify, but as I said before, what we want is to have a robot that respect constraints. So again, we check for safety measures, and we do have a lot of safety nets in the architecture from the robots. Joint limits detections, self-collision detections, etc. We have some hardware stuff that says, okay, the software isn't safe now. The robot goes with hard brakes. For example, inside the AGIMUS Tiago, we have some physical brakes. So we can just say, okay, freeze the robot. That's it.
Okay. Peter?
Yeah, well, I mean, I think what we need to do is to use a technology called runtime verification. What is necessary there is to be able to have properties that can dynamically evolve over time. So you can change them while we are running, so to speak. So it means that you can't validate and verify all possible behaviors at design time. It's something that needs to happen at runtime. And obviously, what's necessary there is to be able to support this in a meaningful way. And that's what we do in our trustworthiness checker, so to speak, in our setup in RoboSapiens.
Okay, thank you both. So let's continue now. Matteo, Richard, and Ganix. What makes humans actually trust adaptive robots? So what do you think we should develop, or you guys should develop, in terms of this industry, that figure that I gave at the beginning, the $20 billion industry that is adopted by humans, and we all follow Elon Musk and his teams and NVIDIA and all this kind of stuff. So what is the deal here?
Yeah, if I may start. Well, I think a bit, of course, will come with habit. No, so being exposed to the robot and so on will, of course, improve the acceptance and trust that you have in them. Definitely, again, some smoothness in the interaction, some safety in the interaction, not to do aggressive movements, not the robot doesn't do something that the human can perceive as a useless motion or too fast. Definitely, this is very, very useful to increase trust in the basically co-workers, let's say.
Yeah, but before the other colleagues respond, we all know that building a good reputation of robotics is going to take a long time, but screw that up is very easy. So as soon as one thing happens, all the media will be watching the industry very carefully. So it's from my perspective as a potential user, I see one of the main challenges that we have, right? So Richard, what is your take on this?
Okay, I think I already pointed towards this before in my previous answer. In my view, we pay too much attention to actuation predictability, as Matteo was saying, and I don't think that's the key to trust. I think the key to trust is decision predictability. When we humans work with other humans, we delegate. We tell the human, no, you take charge of this. So we give them a scope of decision that they can take that we feel comfortable with. And I think that's the way we should approach it with robots. I want to delegate on the robots so the robot has some decision autonomy, and I will trust the robot if that decision autonomy aligns with what I expect from the decisions. So if the robot is not sure it can do something, it will ask me. If it's sure it can do it, it will try to make the decision instead of me. And it is very important that this is an experience-based thing. So it will take a while, like we do with our children. It's exactly the same thing in my view. I have a developmental view on this. You start working with it, you delegate, it does something, I trust it, perfect. I don't trust it, I tell, no, don't do that, please. And we start having this feedback loop. And I think that for humans actually to trust adaptive robots, you need that human perspective on adaptivity, which is the one we have with our friends, with our children, with our colleagues, with our neighbors. And if we don't do it that way, I don't think there's going to be any trust. I don't think you can make rules that can be trusted. It's something that is an interaction.
I can see definitely Richard saying to the robot, "Hey, that's not on my paycheck. It's on your paycheck."
Yeah, exactly.
You decide that, right? You take the risk of that decision. But then you will have to incentivize that somehow. Anyway, Ganesh.
Yeah, just in 1 minute. I remember how an operator we have a code that it said like something like, okay, if this helped me to do my job better, I'm willing to adopt it, right? So first of all, it's that. I mean, it's a colleague, let's say.
Okay.
Then it's true that at the moment, and I have referred, and as Lady mentioned, but yeah, the perceived usefulness seems to be the clear value for daily work, yeah, but also with the decision predictability that has already mentioned by Richard, that I would like to see if for some solution should be bias-inspired or not bias-inspired. Yeah, for some maybe it could be the rule, for some other maybe not. But I will go for I would like to highlight the perceived safety, right? I mean the perception that according to our mindset and scams the robot has, and how we perceive the safety. Yeah, because maybe everything is fine, but the perception that the operator has about the work environment or the workstation is not the proper one. So
absolutely,
yeah.
perception is key for humans. We all know that. So we have to translate that into the robotics. So let's try to wrap up. We have 5 minutes, so we're on time for the last question. And I'm going to start with you, Ganesh, that you finished the previous one. What do we have to do, or what is stopping us for having this safety and trustworthiness segment in robots mainstream? I think Richard pointed something about cultural and ethics somehow is more in the long term, I think. But how can I justify this $20 billion industry that is expected by 2030? Ganesh.
Yeah, I will also. I agree that I don't know if how the safety rules is totally linked with progress in adaptation, but also ethics. Yeah, according to the different frames and different rules from different states and different speeds. Yeah, but I think that the main barrier at the moment is in that point. Yeah, I would say that.
Okay, Matteo.
I think there is still technical problems to solve, basically, and especially when it comes to manipulation, contact, what is normally called the contact-rich manipulation. That's not there, and the current trend is to feed the robot with tons of data, but this doesn't scale up really. So I think there is still something technical to investigate there.
So we have to do our job. Still, we have to do some job.
Yeah,
Okay.
exactly.
All right. Maximilian?
Yeah. In addition, I think that the reliability, the 5 nines gap in perception is important. 5 nines is like 99.999% of reliability. And I would say that a robot performance is as good as its perception in general. And we see it in the VLAs or the VLM. What we call is that how the robot is able to perceive its environment has to be extremely precise. And for now, even a change of lighting during the day or a splash of oil that is reverberating and it's not expected by the robot, it's making a mess in the perceptions. And I think that until we achieve that, we cannot really go mainstream in the sense that it's not going to be reliable enough.
Okay. Richard, your 2 cents. Now you're muted. Richard, you're muted. Sorry.
Okay, I I think in my view, there are actually 2 or 3 things that stopping adaptive robots from becoming mainstream. The first one is a well-established, complete, self-motivated cognitive architecture for these robots. If we want an adaptive robot, we need to have a cognitive architecture that is able to operate with humans. So it has to have all the components that a human expects the robot to be there. And the other aspect is obviously we need to reformulate how we certify robots and trust robots. We cannot expect robots to be 100% perfect. Humans kill humans. Some robots might kill humans. And some humans might kill robots. I'm going to the extreme case.
Yeah.
But it's so if we don't reformulate and in terms of risk and not in terms of perfection, which is how certification is done now, we're not going to have adaptive robots because 100% perfect, we will never get it because there are changes. Things are adapting.
Very good. Peter?
I fully agree with the things that have been said. I think certification is the root cause of what's missing. But I think there are technical issues where, in particular, causality is really what the humans are expecting. So what you are normally seeing is that when you do learning of things, you just learn because of artificial relationship, and that's not enough. And so, but then there's also the angle of trying to include a social angle to things where you need to have different kind of scientists, not just technical people involved, to be able to gain trust, because trust in something you don't know how it behaves is not easy to get. Even if you just have something in your car like autonomous driving capabilities, like adaptive cruise control, you try to tinker with it to try to see, is it really doing what you hope it will do? So there are multiple things.
Absolutely. And I have to say that we, business schools, we have also a responsibility on making this happen. I think through education, through spreading the word of the different gains in the technology and how this is being applied, and incorporating what Richard mentioned at the beginning, ethics and cultural aspects, I think it's also a responsibility for us to make the word of robotics being heard and being understood by everybody. And we're going to keep doing that, that's for sure. All right. Thank you very much, everybody. Right on time, So thanks, everybody, for being there. And that's it. Alex?
I just wanted to take the opportunity first to thank you all for coming, for attending, and the speakers for taking time. And to the attendees, we will email you, obviously. Thank you for attending. And we invite you to join our robotic follower group, where, we'll be invited to special events, more private events and discussions, etc. We'll send you all the links. And also, just before you go next week, we have another event. It'll be a hybrid event. Some of us will be in Antwerp, others will join online, and we'll be tackling into specific use cases that are being done within RoboSapiens. If anybody is, around Brussels, feel free to join us. You're more than welcome. And if not, again, sign up. It's hybrid. We'll have an online version of the event. So yeah, that's it. And again, thank you all so much for your time.